Okay, shall we get started then? Okay, ready, Ashok?
Yeah.
Okay, so it's a great pleasure to have Ashok continue his lecture series. Take it away.
Thank you. Can you see my screen?
Yes, yes.
Okay, thank you. Yeah, so let me begin by writing down where we left yesterday. So we had defined the sixth felicity trace index B6, which was 1 over 6 factorial times trace of minus 1 to the th to h to the 6. And this trace is taken at a fixed charge, okay, and in the center of mass frame, so that the spatial components of the total momentum vanish. Okay. And h is the third component of the angular momentum. So h is the z component of angular momentum. So minus 1 to the 2h you can also recognize as minus 1 to the f. Okay. So I'll begin by giving the proof that B6 does not get contribution from non-BPS states. And so for this, you have to start with the supersymmetry algebra. So the general structure of supersymmetry algebra, if these are the supersymmetry generators, that this is K alpha beta. Okay, let me write it this way. So, and where this one is a linear combination of momenta and charges. Normally, you may not be familiar with the fact that the supersymmetry algebra contains charges, but here you are considering extended supersymmetry. Okay, so that's one way of seeing that it can contain charges. Another way of seeing this is that in 10 dimensions, okay, this would have included various momentum variables here, and some of those momenta actually have become charged after you have compacted, right? Because the momenta along the compact directions appear as charge. So that's another way of seeing why it should contain also the charges. So this is a constant for our problem for given QP and energy. Okay, the spatial components of the momentum, of course, is 0. And it turns out that for non-BPS states, have positive definite K, which means all positive eigenvalues. So all eigenvalue positive. Whereas for 1/4 BPS states, K has 4 zero eigenvalue and rest positive eigenvalue. Okay, and this will become important. This will be important in establishing what you want to establish. So there's a consequence. So first, let's start with the non-BPS states. Here you can take linear combination of the Q alphas. To QM and QM dagger, such that the algebra takes this simple form. QM dagger. Sorry, QN dagger is delta Mn, and QN is 0. Okay, so this is basically diagonalizing the matrix and introducing complex combinations of the supersymmetry charges. So M here, of course, runs from 1 to 8 because the 16 real supersymmetry generators you are making into complex ones. Okay. And we can also choose these Qs in such a way that these have H equal to minus half and these have H equal to half. So from this we can see that they are so now let's consider a non-BPA state. Okay, I got a message saying that my internet connection is unstable. Can you still hear me?
Yes.
Yes.
Yeah.
Thank you.
Would you mind going back one slide just for a second? Because it was.
Yes. So what I said here is that we can assign H equal to minus half to this and H equal to half to this, because that's the question of which ones to declare as creation, which ones to declare as annihilation operators. And I'll declare all the annihilation operators to have H equal to minus half and all the creation operators to have H equal to half. Okay, so let's consider a non-BPA state V of H equal to S, such that the following condition holds, that QM on V is 0 for all M. Then the other states in the same supersymmetry representation are obtained by acting with creation operators. Okay. So they have the generic form I equal to 1 to alpha, where alpha is some integer. So alpha runs from 1 to 8. Okay. So these have H equal to, of course, you start with S, and then each time you act with this, you add half, so it's alpha by 2. And you have to look for all possible ways of choosing these MIs. So using this, we can now calculate B6, which is 1 over 6 factorial. We have to sum over all alpha, so alpha runs from 0 to 8. For a given alpha, there are 8 choose alpha ways that you can choose these QMI daggers. So you have 8 choose alpha. Then minus 1 to the power twice H, so 2s plus alpha. And then twice H to the 6, so 2s plus alpha to the power 6. Okay, so this is what the B6 contribution is for the states that are built from V. Now, this you can do a binomial expansion, okay, and the kind of things, that kind of sum that you need is of the form sum over alpha equal to 0 to 8, 8 choose alpha, minus 1 to the alpha, and alpha to the n, okay, for various values of n. So minus 1 to 2s, of course, you can take out of the sum. Okay. So this one I can write as x ddx to the power n, sum alpha equal to 0 to 8. At x equal to 1. The idea is that every time you act with x ddx, it brings down alpha and it gives you back x to the alpha. So you have, if you apply it n times, you get alpha to the n. But this quantity is 1 minus x to the 8. And now we see that this vanishes as long as n is less than or equal to 7. So this is 0 for n less than or equal to 7, right? Because you need at least 8 derivatives to kill all the factors of 1 minus x, because you are setting x equal to 1 at the end. So this vanishes for n less than or equal to 7. And from this expansion, we see that you get at most powers of alpha to the 6. And this shows that B6 is 0. Okay, so that's the proof that non-BPS states do not contribute to B6. Are there questions?
Hi, just a question.
Yes.
In
go ahead, please.
the sum, why could you restrict to states of that form? As in, why do these states exhaust all non-BPS states?
No, these don't exhaust all non-BPS states. Okay? These form a particular representation of the supersymmetry algebra. You take another non-BPS state and you can again build the tower that way, this way.
But okay, so what you're saying is that any BPS state is of that form for some V.
Exactly, yeah.
Okay.
Because you can, starting with any non-BPS state, you can keep applying the QMs first till it's analyzed by all the QMs. You declare that as V, and then you start building the state from there by acting with Q daggers.
Is it guaranteed that at some point a QM acting on the state, like if I keep acting with QM to lower the level, is it guaranteed that at some point?
Yeah, because QM square is
there will
0,
be a
right?
state that gives me 0?
Yeah, because if you look
yes,
at the algebra, QM square is 0, so you can only apply it once. Every QM you can apply only once.
Oh yeah, so we start with an arbitrary state, with act with QM once, and then that is some V.
Exactly.
Cool, thank you.
Okay, now let's see what changes for BPS or quarter BPS states. So the main thing that changes is that the number of Q alpha, that 4 of the Q alphas actually annihilate all the states. 4 of the Q alphas are identically 0. So basically we have 6 QMs and 6 QM bars. So you repeat the process. And what we get there is B6 as is 1 over 6 factorial. Now you get sum over alpha equal to 0 to 6. Okay, all that happens is that 8 gets replaced by 6. And now this is non-zero, okay, because this is if you repeat a similar analysis, it will be 1 minus x to the 6, and you can apply 6 times derivative because there's an alpha to the 6 factor. And I'll leave it as an exercise to check that this is just minus 1 to the 2s. Okay, in fact, that's the reason why you have chosen this 1 over 6 factorial. This is the normalization that one chooses. So this shows that B6 gets contribution from quarter BPS states. Now, B6 also gets contribution from half BPS states. But they exist only for spatial charges. And we will avoid this. Okay, we will avoid this. Because in any case, the classical black hole entropy, okay, which is q square p square minus q dot p square, right? This is 0 for q parallel to p. So if you are just looking at the regular black hole solutions, then these don't correspond to black holes at all. Okay, so let me now.
When you say this, you will avoid.
Pardon?
So, sorry, when you say you will avoid this, what do you mean? So you will
That
only
we'll
trace
choose
over.
Q and P. That you see, we are fixing a Q and P and analyzing this, right?
I see.
So basically, we will choose Q to be not parallel to P.
I see. Okay, thanks.
We'll analyze B6 only for those charges.
Okay.
Because in any case, for Q parallel to P, this black hole entropy vanishes.
Can I ask another question following up on that?
Yes,
So if we're choosing Q and P and then analyzing the black hole entropy for states with that particular Q and P, why did we need to worry about whether the non-BPS states would contribute to B6? Because they should be in some like other quadrant of Q and P states.
So that's the difference, that both quarter BPS states as well as non-BPS states exist for arbitrary Q and P.
Oh, I see. So you could have
Only for
states
quarter
with
half
the same
BPS
Q
that
and
we
P
need this
that.
first.
So you could have the same Q and P and there be a non-BPS state and a BPS state.
Exactly.
Okay,
Yeah.
got it. Thank you.
I have a question.
Yes, go ahead, please.
Yeah. Is it possible to have one quarter BPS states for Q parallel to P?
I think what happens is that if Q is parallel to P, it automatically becomes half BPS.
I see. Okay.
Okay, so then this is the reason why the B6 acts like a written index for these states, and it cannot jump as we move in the moduli space. But let me just review the argument again. So the first point is that the B6, maybe I should have said something else here. We see that this gives you, this is the representation that we get from here is 2 to the 8 dimensional representation, because those are the number of states that we have. This is sometimes called a long representation. Okay, these are representations of supersymmetric algebra. Okay. Whereas the quarter BPS states, okay, these give you 2 to the 6 dimensional representation, okay, which is also sometimes called intermediate representations. Okay, so these are different kinds of representations. So BPS states, so let me write this. So BPS states or quarter BPS states of 2 to the 6 dimensional representation cannot become 2 to the 8 dimensional non-BPS state, right? Because that will require the spectrum to jump discontinuously. Okay. And a non-BPS state at some spatial point in the moduli space, which is M tau space, may have its mass equal to the BPS mass accidentally, but it continues to have 0 B6. Because the spin spectrum, of course, cannot jump discontinuously, okay, and the B6 is essentially computed from the spin spectrum. Okay. So this basically tells us that B6 does not change as we vary M and tau. Was there a question?
Yeah, sorry. Could you clarify what you mean by 1? What do you mean by that the states cannot become 2 to the 8 dimensional?
Because it requires that the dimension should jump discontinuously. Right?
Yeah, I'm just a bit confused. What you mean is become, sorry. Also, as we vary M tau.
Exactly, yeah.
The quarter BPA states cannot just discontinuously become non-BPS states. Okay.
Exactly.
Okay.
So, so that's why the B6 doesn't change. Okay, so B6 does not change as you vary m and tau, right? This is what I wanted to say. Okay, except in one case, across walls of marginal stability, and I'll explain what this is. This will not play too important a role here in our analysis. Okay, but it's important to know this.
Sorry, can I ask something?
Yes, please.
Are you so B6 for BPS for quarter BPS states just measures number of fermionic minus bosonic states, right? The difference.
That's right. Yes.
So are you saying that as we change m tau, the fermionic states don't become bosonic states? Is that what the claim is?
Yeah, because that will require the spin spectrum to change discontinuously, right? So what can happen is that the fermionic states and bosonic states can combine and become non-BPS. And at a generic point that in the moduli space, that's what will happen. This is again very similar to Whitney index. Right? The Whitney index counts the number of fermionic ground states minus number of bosonic ground states. And you expect that at a generic point in the moduli space, all the excess states have become non-supersymmetric. And only a certain number of fermionic or bosonic states remain. So this is the version of Whitney index, but for particle-like states instead of the vacuum. Okay? The Whitney index was defined to count the vacuum. This index is defined to count the number of particle states, which are supersymmetric.
Also, one more question. H was the z component of the angular momentum in 4 dimensions, right?
That's right. Yes.
Okay. Okay. Thanks.
Okay. So let me explain these walls of marginal stability. So on codimension 1 subspace of the moduli space, a non-BPA, sorry, a quarter BPA state can be degenerate with a pair of half BPA states with the same total charge. Okay. So at this point, the index becomes somewhat ill-defined because these quarter BPA states are marginally stable. Okay, they can simply break apart into a pair of half BPA states. Okay. And one can show that the B6 actually can jump across these walls because the index is ill-defined on the wall. Okay. But the jump can be calculated. Okay, and maybe we'll discuss this again in the next lecture. Can be calculated. And what one finds is that for this n equal to 4 supersymmetric theories, okay, this jump goes as exponential of charge. Okay, the charge could be Q or P or some combinations of those. Okay. In contrast, okay, remember the black hole entropy is exponential of charge square. Because it had this square root of Q square P square minus Q dot P square. So this is much smaller than this. In fact, this is exponentially suppressed. And so for understanding black hole entropy, this will not play any role. Even though there is interesting mathematics behind this, and we may encounter some of these as we go along. Okay, so we'll pretend as if there is no jump because this jump is really tiny compared to the numbers that you are trying to calculate.
Can I ask a question?
Yes, go ahead, please.
This index that you're calculating, if I were to try and understand it from a path integral perspective. Is it an index in the full 4D n equals 4 theory, or are you somehow simplifying it to some easier theory and computing it there?
No, this is the index in full 4D theory.
Okay, and it's the 4D gravity theory.
Yes. Exactly.
Okay, thank you.
Could I ask, what happens
Yes.
to the spectrum? How can we understand what happens to the spectrum as you go across this wall? Before you've been saying, that the spins in the spectrum and such shouldn't jump discontinuously. So how do we get around that here?
Yeah. So what happens here is that some of the quarter BPS states, okay, can be actually described as a bound state of 2 half BPS states. Okay, but this is a bound state with finite binding energy. So this is really a one object. Okay. As we approach these walls of marginal stability, the distance between these two constituents start increasing. Okay. And on the wall of marginal stability, this distance goes to infinity. Okay. So basically what happens is this bound state falls apart. And because on the wall, okay, the index is ill-defined because it's marginally bound, okay, this jump can happen. Okay, basically the state goes up to infinity and disappears.
Great, thanks.
Okay, so let me then proceed. So since you have argued that B6 is independent of m tau, this suggests that there is a way to compare the counting with black hole entropy. Which I'll call microscopic and macroscopic results. So the counting is done at weak coupling. Okay, where actually it's possible. Weakly coupled system, you can, we'll see how exactly it is done, but a weakly coupled system, you can imagine that we can analyze the spectrum and count them. But then to connect to black hole entropy, okay, we increase the coupling. So that effectively G Newton increases. And at some point, the Schwarzschild radius of the black hole, the would-be black hole, okay, we don't know yet if it's a black hole, okay, but if the Schwarzschild radius of the would-be black hole becomes much larger than the Compton radius, then black hole is a more appropriate description of the system. Okay. So we compute B6 by working at weak coupling, and then we go to strong enough coupling so that the black hole description is valid. And so now we can compare log of mod B6 with the Beacon-Stokes entropy plus corrections. Okay. And this also assumes that at a generic point in the moduli space, basically all the only states that remain are the ones that are protected by B6. Okay. Anything that can become non-BPS has become non-BPS. So the degeneracy is really equal to mod B6 at a generic point in the moduli space. Okay. Again, this is similar to what happens in the case of Witten-Idnitz. Okay. You assume that at a generic point in the moduli space, essentially all the vacua which could become non-supersymmetric have become non-supersymmetric. leaving behind only those that are protected by the index.
Sorry, I have a question. So I thought that index is counting the difference of the fermionic and bosonic particle states.
Yes.
But don't you want to count the sum of all states rather than?
Yeah. So that's exactly the statement that I made. That if there is some, say, a combination of fermions and bosons which have 0 B6, then
Yes.
under any small interaction, they typically will combine and become a non-BPS state. Because if a set of states have B6 equal to 0, suppose you have a set of BPS states whose total B6 adds up to 0.
Right.
Then
Yes.
under a generic perturbation, it will become non-BPS. Okay, because there's nothing to protect it from remaining BPS, right? Because BPS requires that the energy takes a very specific value. Now, under a generic interaction, the energy is not energy of a state doesn't remain at a very specific value, right? It changes.
Mhm.
And the only reason that it doesn't change for states that are protected by the index is because the index doesn't change. So indeed, you are right that at spatial points, okay, there may be both fermionic as well as bosonic BPS states whose index cancels. But those combinations we expect will become non-BPS once you switch on generic interaction.
Okay.
Yeah, so that's the general argument. And again, as I said, this is similar to the kind of argument that one uses for Witten index. Okay, so while B6 is the number of fermionic minus number of bosonic minus fermionic states, we expect that a generic point in the moduli space, there is no excess fermion or excess boson. It's either only all bosons or only all fermions, and those are protected by index.
I see. Okay.
There is a better version of this argument that one can give using some version of ADS to CFT1, but we'll see if we can get there. Okay, but this
You're saying is that the black hole states are either all bosons or all fermions.
Exactly. Yeah.
Why?
Because if there are suppose there is some bosonic state and some fermionic state, then a generic interaction will make them non-BPS because they don't have total B6, right? Their B6 is 0. So any excess bosons and fermions will combine to become non-BPS.
Okay, thanks. Yeah.
But as I said, by using a version of ADS to CFT1, one can in fact do a little better. One can argue that the black hole states are actually all bosonic. Okay? And that makes a very specific prediction that the B6 should always be positive. Okay? And this has been tested in various microscopic counting. Okay, but I'll see if we can get there eventually. Okay, right now let's work with this argument that any excess state will always become non-BPS. Is this okay? Are there other questions?
Can I ask a question about the marginal stability while we are on this topic? So you mentioned that the quarter BPS states becomes a bound state of 2 half BPS states. Does that somehow also make the Q and P charges parallel to each other? Because we know that for half BPS states, they have to be parallel.
No, so each half BPS states have their Q and P parallel, but it's a bound state of 2 half BPS states.
Right.
When you add the charges, then they are no longer parallel.
Oh, I see. Okay.
So that's the way it goes. But indeed, each half BPS states have their Qs and P parallel. Okay. So now we are going to, the goal is to calculate B6. But we are now going to use symmetries. Okay, so S and T duality. Invariance tells us that B6 QP should be equal to B6 Q prime P prime, where QP and Q prime P prime are related by duality transformation. So this means that we need not calculate B6 for every Q and P. Every QP, but only for every duality orbit. So duality orbit, each duality orbit is a collection of these charge vectors, which are all related by duality. Okay, and the reason that we need to calculate it for every duality orbit, because inside a duality orbit, different elements have the same B6 anyway, because of this relation. Okay. So then we can ask, what are the inequivalent duality orbits? Well, it's probably not necessary to say inequivalent, because by definition, different duality orbits are inequivalent. Okay, but this is the idea. We want to classify the duality orbits of this theory. And so this.
What is the relation between prime and the Q?
Oh, these are related by duality.
Oh, I see. I see.
Okay, either S or T duality. And so what I'm saying is that because of this relation, we need not, it will be an overkill if we want to determine B6 for every Q and P. We just determine it for one duality orbit at a time. Is this clear? Okay, so now let me give the result for classification of duality orbits for this theory. So we remember the lattice lambda in which the charges take value. Okay. So we first introduce a basis, EI, a basis of lattice vectors of lambda. Then since Q and P both belong to the same lattice, we can decompose Q as some linear combination of these. In P as sum over I, Pi, EI. Okay, so these are integers. So now we define R as the greatest common divisor of all combinations of the form where ij runs from 1 to 28. Okay. So basically this means that you collect all these numbers, 28 times 27 by 2 numbers that come from these, take the greatest common divisor, call that R. One can show that R is invariant under S and T duality. Okay. So R is one of the integers that classify a duality orbit. Okay, you cannot change R by duality transformation. Now, so far, rigorous counting has been done only for R equal to 1 states. So for R larger than 1, there is a conjectured formula, but the counting is not done. Okay, so for this reason, we will focus on R equal to 1. So for R equal to 1, the duality orbit is, I should say, over-specified by Q square, P square, and Q dot P. Okay. So when I say over-specified, this means that it's not that all different values of Q square, P square, and Q dot P are all necessarily on different orbits. Okay. But if you specify Q square, P square, and Q dot P have fixed an orbit. Okay, you don't have to specify the values of Q and P separately, for example. Okay. So this is the result that you are going to use. The other result that you are...
Can I ask you a question?
Yes, go ahead, please.
So basically you are saying from these three vectors, since they're invariant under this transformations, these are the only data you can construct from this all possible P and Qs. And that's why these are the inequivalent numbers you are starting from.
Yeah, so this, okay, this means, let me put it this way, that let's suppose that you have two vectors, QP and Q prime P prime. And let's suppose that both have R equal to 1. Then if Q square, P square, and Q dot P are equal to Q prime square, P prime square, and Q prime dot P prime, they are necessarily connected by duality transformation. And hence they have the same Q and same B6. Okay, so that's the statement. That in the R equal to 1 sector, two charge vectors which have the same Q square, P square, and Q dot P are necessarily connected by duality. Is this clear?
Yes.
Okay. So this means that B6 in this sector is a function of these objects, function of Q square, P square, and Q dot P. Okay. And finally, I should just say, this is something maybe I should have said earlier, but I'll say it now. Okay. This lattice lambda is what is called an even lattice. Okay, it's self-dual, I have already said earlier, but it's also even, okay, which basically is a statement that Q square and P square are even. Okay. So basically, every charge vector has its squared norm even integer. Okay, again, this will be useful. Okay, so now let me turn to the counting. So this counting, I have been stating everything in heterotic string theory on T6. Okay. But the actual counting is in fact done in a dual description of the theory, which is equivalent. Namely, type 2B string theory on K3 times S1 times S1 tilde. Okay, I'll explain what this is. So K3, many of you might have heard of. This is a 4-dimensional complex manifold. Okay, let me not say very much more about this now. If we need something about this, I'll state later. Okay. And these are just circles. Okay, so if we label this by x4 and x5, these are just x4 equal to x4 plus 2 pi and x5 equal to x5 plus 2 pi. And this theory is known to be dual to heterotic on T6. The reason that we do the counting in this theory and not directly on heterotic on T6 is because in this type 2b on K3 times S1 times S1 tilde, it turns out that you can build the black hole states in terms of objects whose dynamics is reasonably well understood. On the other hand, if you are trying to do this in heterotic on T6, then you need objects whose dynamics is not so well understood. Okay, that's why the counting is easier to do in this case. Okay, for this theory, type 2b on K3 times S1 times S1 tilde. But of course, yes, go ahead, please.
Can I ask a question? So then if the counting is easier to do in type 2b, why did we start in the first place in heterotic on?
Oh, that's just because I didn't want to introduce the properties of K3. For example, to count the number of gauge fields and so on, it's easier to do in the heterotic theory. But of course, I could have started with this. Okay, then I have to describe some properties of K3 to count the number of gauge fields that the type 2 theory has.
Got it. Cool.
It's just that. Otherwise, I mean, I could have started from this. Is that okay?
Yes, definitely. Thank you.
Okay. And as I said, we'll do this counting using weakly coupled description. So now let me describe the system that we'll be dealing with.
Sorry, just to ask, weakly coupled in the type 2b frame?
In the type 2b frame, yes. Okay.
That's a question.
So the system,
You said that it's difficult to describe in heterotic because we need to mention talk about objects whose dynamics are not well understood. Is that the NS5 brane?
yes, exactly.
Okay.
We need an NS5 brane to build the system in heterotic side. Okay. So the system that we'll use is one D5 brane along K3 times S1. Q1 plus 1 D1 brane along S1. Then n units of momentum along S1. Now, conventionally, it's written as minus n units of momentum. I just wanted to avoid the minus sign. Okay, so I just call it n units of momentum, but that's just a question of how do you define the direction of S1. Okay, so it makes a difference. Once you have chosen a convention, it makes a difference, the sign, because it's only for one choice of sign that you get a BPS state. Okay, the other choice of sign will give you non-BPS state. So this is something good to keep in mind. Okay, the fourth object is a Kaluza-Klein monopole. And finally, J units of momentum. So these are the various charges that the system carries. Okay. Now here, perhaps most of you have some familiarity with D-branes. Okay, if you are not familiar with D-branes, basically right now let me just say that a DP brane is a p-dimensional extended objects in type 2 string theory, which is known to exist. Okay, so type 2b string theory, for example, has a D5 brane, which is a 5-dimensional extended object. Okay. And we take its directions to lie along K3 times S1. That's what it means here. Similarly, D1 brane is a 1-dimensional extended object. It is made to lie along S1. Okay. These are just momentum that flows along S1 and S1 tilde. Okay. This one I'll explain. Okay, Kaluza-Klein monopole. Okay, because this is a concept which may not be familiar to everybody. But before I go on, let me just say that we can translate these charges on the heterotic side. Okay. And this corresponds to the following quantities following invariants. So R is equal to 1 for this assignment for charges. Okay. Q square is 2n. P square is 2q1 and q dot p equal to j. And because these are arbitrary integers, q1, n, and j, we see that this covers all duality orbits at r equal to 1. Okay. As I said, the counting so far has been done only for the r equal to 1 states. Okay. So even though this looks like a very particular kind of system, using S and T duality, one can show that doing the counting for this is enough to cover all the r equal to 1 states. Okay, because you have covered all values of q square, p square, and q dot.
So is there a way to understand why we need all these objects to construct black hole states?
Well, see, at this stage, you are just using these objects to build the charges, right? And then the idea is that once you have an object with carrying the right amount of charges and its BPS, okay, then once you tune the coupling so that the Schwarzschild radius of the would-be black hole becomes larger than the Compton radius, it does become a black hole. Because as I told you yesterday, that you can get the black hole solution by solving equations of motion, okay? But you can also get the black hole solution by simply requiring that the classical solution has killing spinors.
Mm-hmm.
So imagine that we take this combination of charges and you ask what is the classical background it produces. Okay? And what you can do is that as long as these objects give a BPS state, we can simply start requiring that the classical background has these charges, which means asymptotically, the gauge field should fall off in this particular way, consistent with these charges, and that it should have killing spinor, and you will basically get the black hole solution.
So for instance, why do we need this 1d5 brane? It doesn't have any charge or...
Oh, because q square is obtained as a product of this d5 and this one. If you didn't have the d5 brane, you will get a product of q1 with 0, and that will give you 0.
I see. Okay. Okay.
So these ones are necessary because you are actually taking products, right? P square is 2q1. I mean, you can ask, this is quadratic, how can it become linear, right? And that's where these ones play a role. Okay, one Caruso-Klein monopole and one d5 brane is the reason why you have linear.
Okay, thanks.
Variability.
So I have a two-part question. So just to make sure I understand, the reason that we've picked all these objects here is to engineer the right charges to get the duality orbits on the heterotic side, right? So we know what we want on the heterotic side and we pick the right objects. But if we could have been able to do like the counting of the gauge fields and everything directly on the type 2b side, could we have decided to use simpler objects like black holes of D3 branes only or something?
Well, you could use other objects, but that doesn't have to do with heterotic or type 2 because the duality group is the same in both because they are equivalent theories, right? So type 2 has exactly the same duality group, SL2Z times O622Z as heterotic. Okay, it's just the duality group acts differently.
Mm-hmm.
So
what goes wrong if you just choose D3 branes?
Well, it's just this is easier, right? I mean, in fact, there is counting available, okay, at least for some set of charges where it's built purely from D3 branes. You don't need any momentum or anything else. Just take intersecting D3 branes and you can build a system. Mm-hmm. But the counting there is much more difficult. Okay, the counting has not been done for generic integers, but for some special cases. Okay, this I'm not saying that there is a proof that this is the easiest system, but at least this is one case where one can do the counting, right? And that's why you choose it.
Got it. Thank you.
Can you explain how this restricts you to R equals 1?
Okay, so let me now say what is the Caruso-Klein monopole. Okay, because this is something that may not be familiar. Okay, so KK monopole associated with S1 tilde. Now, remember, so let's say S1 tilde has coordinate x4. Okay. So G4 mu is a gauge field in 4 dimensions, right? Well, we did that thing for heterotic, but as long as there is a circle, the G4 mu will be a gauge field, right? Both in type 2 as well as in heterotic. So circles always produce gauge fields on a metric. Okay. So the electric charge under this is the momentum along x4. Is carried by momentum along S4. Okay. They produce along X4. Okay, let me call it S1 tilde. So KK monopole is a classical solution that is magnetically charged under G4 mu. Okay, that's what a KK monopole is. This is also called the Taub-Knot space. Okay, and I'm going to write down the metric in the next slide. Okay, but physically that's what KK monopole is. It's an object that carries magnetic charge under G4. So solution. Okay, sometimes we can refer to as KK monopole or sometimes as Taub-Knot space. So here it is. R0 is just a constant. So R0, as I've already said, is constant. And there are some periodic identifications. So these are the periodic coordinates, theta, angular coordinates, theta, phi, and psi. So the identification is theta, phi, psi is equivalent to 2 pi minus theta, phi plus pi, psi plus pi by 2. The same as theta, phi plus 2 pi, psi plus pi, and that's theta, phi, psi plus 2 pi. Now you may ask, what does it have to do with compactification in S1 tilde? Okay, so for that we have to just look at the R goes to the larger limit. Okay, so R equal to 0 is at the center of Taub-Knot. Okay, that's the center of the monopole solution. Okay, but to see what space it is embedded in, we have to really go far away from the monopole. Okay. So as R goes to infinity, okay, let's look at the solution. Okay. So this becomes dr square plus r square d theta square plus r square sin square theta d phi square. You can recognize this as a 3-dimensional Euclidean space. These are just the transverse space to the monopole. Okay. And then we have R0 square times 2 d psi plus cos theta d phi whole square. Okay, so psi is a compact coordinate, right? That's what labels S1 tilde. Okay, and this one, okay, see this one, what basically this means is that G, if you identify psi as x4, right, this says that G4 phi is cos theta. Okay, so this is a phi component. Okay, the phi component of the gauge field is cos theta, and you'll recognize that that's precisely how a monopole behaves, right? The a monopole solution has a phi component of the gauge field proportional to cos theta. Okay, that's what shows that it's actually magnetically charged under G4 view. Okay. But this is a full solution. Are there questions? Okay. Now, one important property of this.
Sorry, one question. This
Yes.
solution is a Euclidean, right?
Yes.
In 4D, shouldn't we looking for a Lorentzian solution? This may be
Yeah.
very
So
naive
you just
question.
add a minus dt squared to it.
Oh, okay,
So this
okay.
is a part of the solution that gives the, because these are static solutions, right?
Mm.
So this is the part of the solution that gives the free transverse space and the compact circle S1 tilde.
Okay, okay.
Okay, because a monopole solution has to have this some kind of warping because you are carrying magnetic charge. And with this, you add time coordinate S1, K3, everything else is added to it.
Sorry, this is a solution
Okay.
when we only have the monopole. But when we add the D5 brane and the D1 brane, the solution changes, right? Or
Yeah. So we are not trying to attempt. We are not going to attempt to write down that solution because that will be just a black hole solution in 4 dimension. I wrote this to just say what a Taubner space is. Okay, or the Karuzi-Klein monopole is, because there's some property of the solution will become important for us.
Okay.
But you are right that the full black hole solution, of course, is not just this. Okay, so we'll now examine the metric near the center. Okay. Now you see that the metric looks singular at the center because there is one of our RPs here. Okay. But that singularity is actually a coordinate singularity, and we can write down, make a change of coordinate, okay, to remove the singularity. Okay, so I'll describe now the metric near the center. Okay, so for this we define new coordinates. We trade in 40s. Okay. And what one can show, sorry, I again got a message that my internet connection is unstable. Can you still hear me?
Yes.
Yes.
Thank you. Okay. So in these coordinates, the metric actually looks flat near the center. Okay, so this is flat, Euclidean. But the property that I want to emphasize here is that if you look at the psi goes to psi plus alpha transformation, okay, just shift in psi, this corresponds to equal rotation in x1 tilde, x2 tilde, and x3 tilde, x4 tilde planes. Now the northern charge associated with psi goes to psi plus alpha is of course the momentum along S1 tilde. And this is angular momentum. So this, of course, this corresponds to particular component of angular momentum. So this is going to be important because remember that our system should have some angular should have some momentum along S1 tilde, the momentum J along S1 tilde. Okay. And because of this, we'll build it by putting things at the center of tau naught, okay, and imparting angular momentum on those objects. Okay, because the angular momentum at the center of tau naught can become momentum along S1 tilde. Okay, a particular component of the angular momentum, okay, which is dual T equal rotation in these. Okay, so since we have these relations, q square is 2n, p square is 2q1 tilde, and q dot p equal to j. Okay, what we want is to compute b6 as a function of q1 tilde, n and j. Okay, because these are the p square, q square, and q dot p values. Okay. Now, as in any statistical mechanics problem, okay, instead of doing this counting of states for a given set of charges, okay, it is simpler to first compute the partition function. Remember, this is the way we study ideal boson-forming gas, right? Even if we want a microcanonical ensemble results, okay, fixed number of particles, fixed energy, and so on, okay, we first calculate the grand canonical partition function and then go from there to microcanonical results. Okay, and we're going to do the same thing here, okay, except that here we'll use exact transformation from partition function to B6 without making any approximation. At least it is possible to do that. Okay. So we define the partition function j z rho sigma v as sum over q1 n and j. Okay, these are all integers. -1 to the j b6 q1 n j, and then exponential 2 pi I times q1 rho plus n sigma plus jv. Okay. So once you have computed z, okay, we can get b6 z by Fourier transform. Okay, so you are not giving up anything. Okay, it's just a z is a little easier to calculate first, and that's what we'll do.
So when are we going to impose quarter PPS condition that the states have to be quarter PPS?
When you do the counting.
So far we haven't.
To ground states.
Okay.
I'll mention where we are going to actually use it. Okay, when you do the counting.
Ashok, you have 5 minutes left.
Okay, thank you. Okay, so we are going to work at a generic point in the moduli space. At a generic point in the moduli space. And here something nice happens at a generic point in the moduli space. Okay. So what happens in this case is that at a generic point, okay, the D1 brain, first of all, is bound to the D5 brane. Okay. You can think of as if the D1 brane is stuck to the D5 brane, okay, which means that it can slide along the D5 brane. But cannot oscillate in the transverse direction. Okay. Now here, when I say it cannot oscillate in the transverse direction, of course, if you put energy, give it enough energy, it can move in the transverse direction. And that's one of the places where the BPS condition comes in. Okay. We are looking for the lowest energy configuration, okay, for a given set of charges. And you have to avoid doing things that is not necessary. Okay, so you don't allow the D1 brane to oscillate in the transverse direction, because the minimum energy configuration is when it slides along the D5 brane. The second thing you find is that the D1 D5 system as a whole is bound to the center of tau naught. Okay, again, not a generic quantum moduli space, because there's a potential generated for the D1 D5 system that binds it to the center. Okay, again, I mean, of course, if you give it energy, then you can move it away. Okay, but that will make it on BPS. So in this case, what one finds is the following. So one finds that we can regard the system as three independent systems. Okay, this is very similar to when you have a complicated dynamics, but you can decouple some of the degrees of freedom. Okay, like for example, when a rigid body falls under gravity, okay, the center of mass motion you can decouple from the relative motion in the inside the object. Okay, so it's similar. So when I say three independent systems, that's what one means. So the first system is D1 brane motion. Inside D5. The second one is D1 D5 center of mass motion inside tau naught. And third one is the dynamics of tau naught. And when the coupling is small, then the coupling between these systems is small, okay, which basically means that the partition function factorizes. Okay. It can be written as a product of three independent partition functions. So one is I'll call ZD1, that's that D1 brane motion inside D5. Okay. Then we have the center of mass motion, okay, the D1 D5 system inside tau naught. Okay. And then the dynamics of tau naught itself, which I'll call ZKK. This is the KK monopole dynamics. Okay. So what we'll do next time is to calculate each of these separately and then take the product. Okay. And we'll discover that the product, in fact, is nicer than each individual components. Okay. But this is the way the counting will be done. Okay, so I think my time is up, so I'll stop now. Are there questions?
Okay. Thanks a lot, Ashok. But yeah, so let's take a couple of quick questions, and then maybe after that we can transfer to Gathertown. So.
I have one question. These states look like they're built out of a lot of different pieces in the type 2B description. Do they look any simpler in the heterotic side, even if they're harder to calculate with?
Yeah, in the heterotic side, you can build them from again KK monopole, NS5 brane, and some momentum and winding along the compact circuits.
Okay. Thanks.
Yeah, so the description is, I think, a little simpler in the heterotic. But because of the NS fibrant dynamics not being well understood, the actual counting has not been done in the heterotic side.
Any more quick questions?
Can you explain how the description in the type 2 string theory, you know that you're restricting to R equals 1?
Oh, what we can do is that each of these charges you can convert to heterotic side, because there is an explicit map between any charge on this side, on the type 2 side, to any charge on the heterotic side. Okay. So you use this duality map to convert these into some combination of Kalb-Klein monopoles and NS fibrants and moment and winding on the heterotic side. Okay. That gives you Q and P, and then you calculate explicitly this GCD.
So if you're interested in like R greater than 1, presumably you need some other collection of objects?
Yeah, basically what you have to do, okay, let me see if I remember correctly. One way to make R equal to 2, for example, is that you take 2 Kalb-Klein monopole and then this J, replace also this J by 2J, twice, an even number. Or 2D5, 2Q1 plus 1 D1 and 2 N units of momentum. Okay,
Great,
so that will
you.
be one way. These are the 2 ways you can get R equal to 2. Right? If you want to general R, you basically take them multiples of that R, the numbers. And the reason that is difficult is because if you, for example, try to take multiple Kalb-Klein monopoles, okay, then it has a singularity when they coincide. Okay, 2 Kalb-Klein monopoles in the modular space, there is a singularity when the 2 Kalb-Klein monopoles coincide, and that dynamics is not well understood. On this side, right, if you have a common factor between the number of D fibrant, number of D1 brands and N, again, that dynamics is not well understood. And that's the reason the counting for R equal to 2 is not available. But if you are asking, can you figure out what are the charge assignments that you need for R equal to 2 or any general R? Indeed, you can. Does that answer your question?
Yes, thank you.
Alex, we couldn't hear you.
Oh, sorry. Professor, do you have a good reference for this construction of the K3S1 embedding into the heterotic model?
Yeah, I think if you look at the review that I mentioned yesterday, it's in fact also mentioned in the document that I have put on the wiki page. You will find the references, and I mean that is more like a survey, but there also you'll find all the original references where you can see this map.
Pardon me, thank you. Sorry.
Professor, are we staying away from the points where the gauge symmetry enhances, or can we still deal with those?
Yes, you are at a generic point in the modular space, so you are staying away from any spatial points. Because once the gauge symmetry enhances, the dynamics becomes much more complicated. Right? And in fact, on the type 2 side, right, the gauge theory, gauge symmetry enhancement basically says that the K3 becomes singular.
Yeah.
Yeah, so you are staying away from those points.
Okay, if there's no more quick questions, then let's thank Ashoke again.
Thank you.
Thank you.